All participants will be in listen-only mode, and you can type questions for the presenter or technical questions in the bottom left-hand chat box. I will respond to them directly or post the questions to our presenter. We are recording this webinar today, as you heard, and we'll be posting the recording along with the PDF of the presentation on the SECOORA website. We are very, very excited to welcome Ian Walsh from Seabird Scientific as our speaker today. He will be presenting A Year and a Hurricane Apart, Nutrient Loading in the St. Lucie Estuary in the summers of 2016 and 2017. Ian Walsh received his master's from the College of Oceanography at Oregon State University and PhD from Texas A&M University. His research interests are particle dynamics, including the use of the particle field to understand basic biogeochemical processes and the influence of physical forcing on those processes, carbon fluxes, and states, including predictive modeling and the development of imaging tools for in situ measurements of particle abundance and size distribution. Ian, thanks so much for joining us. I'm going to go ahead and turn the controls over to you, and you can share your presentation.
Cool, thanks, Abby. Okay, so you should all see my intro slide. And now I can't see chat or anything. Let's see if I can hang on. As I adjust my desktop. Okay, I'm going to continue on. We're talking about data from algal blooms and within the St. Lucie Estuary. This is data from the Indian River Lagoon Observatory network. It's run out of Florida Atlantic University. And really this whole endeavor, all of the data we're going to present today and what we learned last year is built upon the work of Dennis Hanasak and Kristen Davis, and also discussions with Brian LaPointe. So they really are the people who are doing the hard work to get us all this data. We're just sort of looking over their shoulders and kibitzing on it. So a year ago, there was some very heavy algal blooms in the estuary that caused a state of emergency to be called and a lot of consternation among the people who lived in the estuary. And since it's a very big tourist site, that also had a decided economic impact to the people living there. And I started getting interested in it because we have Seabird Scientific provides the instruments and the LOBO systems that are being run by the IRLON site. So today we're going to cover a fair amount of ground. I'll try to go at a good pace. But certainly ask questions, and this will be available later. And also, I'm not disappearing, so you can ask me questions directly afterwards. So we're going to cover a very wide range. We're going to talk first about how estuaries work and the biogeochemical processes, mainly the ones that I'm interested in, particularly with sources of nutrients. We're going to look at the estuary itself and how I got the data, because I think with live data systems, it's important to show how the data is available to you, especially if you're students or not scientists who do this regularly. That can be somewhat intimidating to try to just get the data, but really it's fairly straightforward once you work your way through it. We're then going to cover the ground that we covered last year in discussions about the harmful algal bloom. And then we're going to compare that to data from this summer. And finally, we're going to end up with this September. And the last few slides of this presentation were downloaded literally about 40 minutes ago. So we have data up to the hour to discuss, which is just one of the coolest things about systems like this, is that we have live data that anyone can look at, and you can become obsessed with them if you avoid it. During hurricanes, during storm events, and other events, the ability to sit at your office or at home and look at real-time data from within the water system is, frankly, a phenomenal ability that we have that was certainly not available when I started doing this work. many, many years ago. Okay, where are we talking about? We're talking about the St. Lucie Estuary. It's on the east coast of Florida, pretty much for a couple of years ago. The only thing I knew about Indian River was that's where you got grapefruit from, and St. Lucie is the winter home of the New York Mets. But it's a vibrant estuary. You can tell from the picture here that lots of people live there, and to the southwest is Lake Okeechobee. Lake Okeechobee is essentially a catchment lake for a lot of the water that flows, that lands on Florida, flows to the south, and instead of going down to the into the river of grass, the Everglades, a lot of it is pushed over to the Fort Myer estuary to the west, and then periodically, when it gets very high, some of it comes into the St. Lucie Estuary. The pins on here are the LOBO sites, the Land Ocean Biogeochemical Observatory. Those are the instrumentation platforms that were developed out at MBARI, the Monterey Bay Aquarium Research Institute, licensed through Bird and Atlantic, and provided to Florida Atlantic. So an estuary, it's where the fresh water meets the salt water, and really you can think of it as a big mixing tub. The energy is supplied by, the energy and materials, particularly nutrients, are supplied by fresh water running downhill, and the seawater is driven by the moon. Here's the sort of the basin structure that we're going to look at, and this is pretty much what I've just put together. This has got nothing to do with other people's work yet, but it's a good overview and just the way I'm looking at it. We're looking at the mouth of the estuary, and the LOBO there is the SLE, St. Lucie Estuary. We've got the middle basin here. We've got the North Fork, the South Fork, and the South Fork 2. The South Fork 2 is where the canal that empties out from Lake Okeechobee enters the estuary. So that's our lake source, comes from here, and our ocean source comes from the mouth. Okay, as I said, water flows downhill. This is just a quick and dirty cartoon of how those basins line up hydraulically. The water comes in from the lake at SF2 and essentially runs downhill to the mouth of the estuary. But downhill changes within estuaries. We can look at the head, which is the difference between the height at SF2 and the ocean sea level. And while sea level is a nice concept, it changes. And that's driven by our tides, where we get high tides and low tides on a daily basis. And in fact, it's twice daily. But we also see storm surges occasionally, especially associated with hurricanes. And then also associated with hurricanes and other rainfall events, we get the freshwater height also changes. So high rainfall, high outflow, high runoff. If you dump a lot of fresh water onto a fairly level platform, it's got to go somewhere, and it heads to the estuary, and that effectively changes that gradient. So our tides and our storms change the gradient within the estuary, and that's significant because the higher the gradient, the more mixing, and also the lateral progression of the saltwater intrusion. So if we've got low tide, then it's mostly freshwater. High tide and then storm surges, we get a lot of seawater intrusion, and essentially it makes its way further and further into the estuary. So for plants, and our particular interest in this one is sort of explaining why that harmful algal bloom happened, is that plants need light, nutrient, and time. Well, Florida has plenty of light. This is a graph of the annual cycle of the photoperiod, and we minimum is about 11 hours, maximum is about 14 hours. So, as a good subtropical system or lower mid-latitude system, there's plenty of light available for plant growth. Characterized in the area, we got, as you can see, plenty of insolation, 3.5 kilowatt hours per meter square per day, max in January and December, maximized in May at about 7. Mostly clear days. Temperatures are warm. Precipitation is high all the way through the year and maximized in the summer. So you've got warm year-round and wet summers. So plenty of energy, plenty of light and plenty of high enough temperatures for plant growth. So the limitation then really becomes down to what's our nutrient values and the time that the plants have to grow. So one of our M members, of course, is the ocean, and the ocean is, not surprisingly, salty. I just pulled some data from a robot system, biogeochemical systems that are built off of the Argo platform. This was data from one run out of the French Institute. And you can see in this slide, our profile of the ocean is about 35 PSU, practical salinity units. So the ocean is very salty, and that's one of our end members. It's also very low in organics and relatively low in nutrients at the surface water. So here's a profile of the dissolved organic matter in the ocean on the left, and on the right is the nutrient concentration in nitrate. And this is the same technology that's taking this data set, which is an inversion of the UV absorption spectrum to get nitrate. It's the exact same technology that's deployed on the IRLON LOBO systems for that. That's, again, another Mabari Monterey Bay Aquarium Research Institute technology licensed by Atlantic and Siebert Scientific. So, looking at an estuary, we've got fresh water, we've got ocean water. Fresh water has a large amount of dissolved organic matter and high nutrients. Ocean water has a high amount of salt and low nutrients. So we're going to use those two end members to watch the changes within the estuary and then make some predictive, observational and then perhaps predictive responses to that. But first, you got to get the data out. You can get the data from the IRLON data access on the SECOORA website. Go to the SECOORA portal.secoora.org, and they have a very nice system which has got an interactive map on it on the lower right-hand side. If you go to there, you'll see, I actually zoomed in, you'll see a much larger picture of the entire SECOORA area, lots and lots of dots. Here I've zoomed in to eastern Florida and the IRLON sites. I've hovered my mouse over the St. Lucie Estuary South Fork Lobo, and it'll pop up the current conditions. This is a couple of days ago, current conditions. It's really a nice interface, really useful for looking through at what the live data is available. But it's also not one that I'm terribly familiar with. So I'm much more familiar with the LoboViz, and that is the direct out of Florida Atlantic. So we're gonna look through that just to show you how I got the data. So that's at fau.loboviz.com. Here's the website opening page. Nice picture of the campus. Map to the right that shows where the Lobos are, and you'll see that they run all the way up almost to Melbourne along the Indian River Lagoon. We're concentrating down at the Port St. Lucie area of the estuary. So we're going to go to the LoboViz page off of this page. Just click on that, and that brings up a graphic of the sites listed that we have available data from, and our X variables, generally just leave that at date, all the different instruments that are on the globo systems and in different unit structures, and our date range. So the first thing I'm going to do, because what I'm really concerned with here is getting the data and getting it in a uniform mode so I can dump it into a spreadsheet for further processing. I'm going to unclick all but one site, and because I'm very linear, I'm going to start with the bottom and work my way up. You're only going to see the first one, but rather than start in the middle and then download the same one over and over again, I find it easier to work on one end and work my way backwards, or the other way around. Okay, I'm going to leave it on the X variable on date. I'm looking at all the changes with time. I'm going to pick the Y variables that I want, and I open up the weather part of it, so I'm going to get air temperature, rainfall, solar radiation, a lot of the drivers of what causes the biogeochemical responses. I'm also picking units that I'm familiar with or find easy to work with. So chlorophyll is in micrograms per liter. I want my current speed in millimeters per second. On the other hand, I do want my rainfall in inches because I'm used to inches, and millimeters rainfall doesn't make, I don't have an intuitive sense of that. So I've selected the data here. Then I'm going to set the time range. In this case, I'm just leaving it on a week ending on the end date. That's already programmed in. So whenever you open this up, in this case, it was September 29th, that will be on there. And then click the plot the data button. And what you get is sort of a terrible looking plot because I've picked all the data. It would be much better to just plot one at a time if I was going to visualize it. But in this case, I really only want the data, so I don't really care what the plot looks like. Then I'm going to download the data. You can download it as a data file with a tab delimited structure, or data as text. And here's what that looks like when you expand it. This is the data as text, and you'll see it's just as it says. It's data as text and lots of data. The amount of data that's produced by these systems is actually phenomenal. And this is 1 hourly data point. That's actually an average of a fair number of data points that each of the instruments is taking, and it's doing that round the clock. And it's been doing it, I think, for 3 to 4 years now. Okay, I take that data set, I download it into an Excel spreadsheet that I've already pre-configured with the different station names and charts, etc., so that they sort of update as we go. If you want this, it's not terribly pretty, but it does have a lot of the structures. I can make this Excel spreadsheet available to anyone if they just send me an email. Okay, so that's how I got the data, and I want to point that out because the whole point of this live data is to get it out there so that people start to use it. SECOORA and all of the member institutions are dedicated to bringing that data to the public, and the public, not just researchers, not just people who really know what they're doing, but anybody who wants to do something with it. And that includes fishermen, researchers, tourists, etc. And I think what we'd really want to see over the years is not just people taking this data and looking at it, but taking this data and turning it into products. And part of the game here is to make sure that we can collect data like this for the foreseeable future. And at the moment, Kristen and Dennis have to write proposals quite often in order to keep this funding up. And if we want to be able to predict and react to harmful algal blooms and perhaps even prevent them, we want this data available all the time. So the best thing to do would be to have a nice, stable funding source for it to keep going forward. And a stable funding source would allow Kristen and Dennis to spend more of their time looking at the data and less of their time asking for money. So I'm going to get off my soapbox now and continue the data. So back to 2016. We're going to talk about 2016 now. And basically, it was a very mucky situation. I love that photo on the left. Someone described it as guacamole soup, and that looks perfect. But not something you'd want to go visit, not something that you'd want to swim in, and God forbid, I'm sure you do not want to smell that either. Okay, so where are we again? We are down on East Coast Florida. Here's our St. Lucie Estuary. These are the sites, and for the most part, I'm going to keep these symbols the same. However, I am colorblind and assembled these slides over a year, so there may be errors in presentation. Here's Lake Okeechobee to our lower left, and here's S308. That's the gauge station that allows water to flow from Lake Okeechobee into the St. Lucie Canal when Southwest Florida Management District and the Army Corps of Engineers deems it necessary. Okay, so a year ago in the summer, this was the situation before and during the HAB. Quite a bit of water was being discharged in a fairly continuous stream for the entire month. So all of the month of June was running between 1,500 and 2,000 cubic feet per second. Then, as we got to the reaction of people seeing the HABs and also, not coincidentally, the 4th of July weekend, they dropped the flow for a bit. Okay, so now we're getting plenty of flow in from Lake Okeechobee. I guess I haven't mentioned this. Most of the discussions on the HAB in Lake Okeechobee is that Lake Okeechobee is a huge source of nutrients to the estuary, and that nutrients and quote-unquote toxins are causing the harmful algal blooms. So I took a look at the data. This is a plot of our CDOM, the color dissolved organic matter, on the x-axis, and on the y-axis, salinity. So this is what I'm trying to do is look at where are sources of nutrients, and first I want to know where the sources of water are. So I've got seawater, which has very low CDOM and very high salinity, and then I've got, at this point, Lake Okeechobee water, which has high CDOM and low salinity. But what was interesting was that it's not two mixing regimes. It's not Lake Okeechobee and seawater. There's a third M member, which has relatively low to brackish saltwater salinity loading, but very high CDOM loading. And that's really runoff and other freshwater sources. So not directly coming out of Lake Okeechobee and not down through the canal, but from just general runoff from the rest of that urban environment around the urban and agricultural environment around the estuary. If we look at January of 2016, that was a month in which there was very little flow coming down the canal. You can see that much more dramatically. It was also very wet. So in January 2016, again, we're just trying to characterize our end members. Here's our seawater, and here's our runoff. And the Lake Okeechobee was not much of a significant factor at that time frame. But in June and July was the time when we were seeing the HABs at the site. Now we've got essentially no runoff, lots of Lake Okeechobee water coming in, lots of high salinity water. But notice that before, where we saw mixing along between the M members, we don't really see mixing. We see in the middle estuary there's some salinity, but now we've got North Fork, South Fork, and the South Fork 2 is buried under all of this. It's basically fresh water. So then when we look at the phosphate, the nutrient loading, and we look at phosphate because phosphate tends to be associated with harmful algal blooms. In fact, this morning on the front page of the New York Times, at least the electronic version, is an article on an enormous harmful algal bloom in Lake Erie triggered by phosphate. So this is not just the St. Lucie Estuary. This is a somewhat worldwide phenomenon where there's excess phosphate. There tends to be blue-green algae. But remember, you also need not just the phosphate. You need time, and you need light. So here's our 3M members. Here's our North Fork. We've got very high phosphate. Here's the black circles are what's coming in from Lake Okeechobee, relatively low phosphate. And here's our and remember from the seawater, even less phosphate. So our tracers that we talked about earlier, fresh water, high organic matter, high nutrients, ocean water, salts, and low nutrients. When we look at what we were looking at in 2016, the characterization of the ocean now, 35 PSU, 10 ppb quinine sulfate. Think of that as just a marker for dissolved organic matter that we can use to compare instruments. And then phosphate, less than 1 micromolar. Lake Okeechobee, very low salinity as expected. CDOM at about 60, and somewhat unexpectedly, to me at least, just 1 micromolar of phosphate. The runoff, brackish water, 10 PSU, very high CDOM, very high organic loading, and a relatively high compared to the other two sources of phosphate. And this was, to people who knew the estuary, this was not a momentous discovery. This is what they've been talking about for years. So Brian LaPointe, who I talked about this with, has a series of papers, this one from 2012 on the phosphate loading, this one very specifically on sewage-driven eutrophication and harmful algal blooms. That's from 2015, and then a 2015 report to the local council. So not unknown, just had not reached to the point of becoming the lure of the land. Instead, Lake Okeechobee was being blamed as the source of the nitrates. So now when we're looking at the data, we're really looking at the nutrient loads at the sites, and we'll dig into it a little bit deeper. We're going to look at the phosphate and the nitrate in situ data from the instruments on the LOBA. So we have a phosphate sensor that does wet chemistry, and we have the SUNA, which takes the inversion of the UV absorption data, and it calculates nitrate from that. What I've done in the plots that are coming up is I plot phosphate and nitrate with time during the June and July period, or zoomed into the late June, early July. And I've taken the axes and micromolar and put them into the Redfield ratio. So the Redfield ratio is the molar ratio of the nutrients in your average plant in water. That ratio works out to be about 16 atoms of nitrogen for every atom of phosphorus. That can change with a lot of different things, so it's somewhat of a global average, but it's a useful tool to look at when the water is relatively enriched in phosphate relative to nitrate. And when we do see relatively high levels of nitrate relative to the, phosphate relative to the Redfield ratio, that's when we see blue-green algae outcompeting the other phytoplankton. Okay, so here's our South Fork 2. This is the Lake Okeechobee. This is late June, early July. On the x-axis, phosphate on the left y-axis, nitrate on the right axis. So where we see phosphate above, except I've got that backwards, where we see nitrate above, then we're not enriched. Where we see phosphate above nitrate, then we are enriched in the Redfield ratio. So these are relatively low, 1 to 2 in the phosphate, and about 20 to 30 in the nitrate, micromolars of nitrate, and no great signal here. But we go to the North Fork. Now we see very high phosphate, tidal signal in the phosphate that seems to dampen as we go on with time. Here's a tidal signal in our data early on in the signal in the nitrate. There are a few spikes in the data. I have not done any QA/QC on the data. Did not try to remove any spikes. This is relatively raw data, so you'll see occasional glitches. Okay, and then we go further down. So now we're going towards the mouth of the estuary. And here we see the middle estuary. Now phosphate is lower. That ratio is highest in the North Fork. It's lower here now as we moved our way to the ocean. not unexpectedly, we get to the ocean, and phosphate in the early part of the period is relatively high, very tidally driven. You can see the nice tidal signal, and the nitrate is totally tidally signaled through the entire time period. So as we work our way through, we note that there's a tidal signal. The phosphate is relatively enriched relative to the nitrate, and that dampens out as you go towards the ocean. So all of that is not unexpected. But what was unexpected is that we see some curious spikes in the South Fork Lobo. So our whole idea here is that our salinity values should be inverse to our nutrient values. So if we've got high salinity, we should have low nutrients. But in fact, for a period of time at the South Fork Lobo, when the HAB was occurring, we got a positive correlation between all three of our end members, salinity, CDOM, and phosphate. So just here's the South Fork data set, again, late June, early July, and you'll notice all those spikes line up very nicely. This is phosphate and salinity, and this is CDOM and salinity. So what's going on here? Back to our basin relationships. This is what we would see just looking at it. Here's our salt water in the blue arrows coming up into the estuaries on the high tides, and our fresh water flowing out, particularly on the low tides. So this was what we would normally see, and what we think we're seeing is that at times of high discharge, we don't really get any flow up into the basin into the North Fork and the South Fork from the ocean. So this becomes mostly just fresh water. And with just fresh water, what that really indicates is that water is staying around there for a fair amount of time. So it's not flowing out, it's not getting diluted by the ocean water, it's spending a few days there, and that gives the blue-green algae time to double a few times and become that real guacamole mess that we saw in the pictures. And we can tell that because that's what the salinity data shows us. The salinity data is only getting into the middle estuary. It's not getting into the South Fork and the North Fork. So that's the result when you add a bunch of fresh water in it. It's not the nutrient loading that's coming out of the lake that's causing the problem. It's the freshwater flow itself and the fact that the estuary can't process that flow and get it out fast enough. So essentially that flow becomes a plug in the discharge. So we made a couple of recommendations at that time as to ameliorate the situation, and not surprisingly for a scientist who works for a company that sells instruments, one of our conclusions was we need more data, and that we need more instruments. And I still think that's true. I think it would be very helpful for this analysis if we had a LOBO system at the discharge point at Lake Okeechobee so we could see the delta as we go there. And also to the north, we really don't have a whole lot of data of the flow from the north directly from the canals into the North Fork. But what we really concluded was if you want to decrease the appearance of harmful algal blooms in the estuary, they should modulate the discharge, alternating periods of high and no flow to keep the ocean water flowing up into the North Fork and the South Fork and diluting and moving the fresh water out. So remarkably, and probably coincidentally, that's exactly what they did. So now this is our discharge from 2016 from the HAB period all the way through October, and you can see we don't have a month anymore of constant high flows. Now they've modulated so that on a weekly basis it goes high and low, highs and lows, highs and lows, even when the total discharge is about the same as this period. The modulation is pretty extreme. And in fact, since this time period, there have not been the large harmful algal blooms in the estuary that occurred in late June and July. So to summarize, the live data from the IRLON helped us, literally drives the understanding of the estuary. The ability to look out your window, even if you're 3,000 miles away in Oregon, and postulate what's happening in the estuary and look at the data that tells you what's happening in the estuary is an amazing tool. Discharges from Lake Okeechobee seem to alter the estuarine circulation. It would be nice to get a model going and run this so that they know that. And then finally, it's much more likely that higher freshwater residence time and excess phosphate leads to bloom rather than just the dumping of phosphate into the estuary itself. So that's 2016. So 2017 is a pretty cool contrast. So this is our flow for 2017 from May through now, well, a week ago or so, when I grabbed the data. This is from the USGS website, the S308 discharge. You'll note that a lot of it is negative. So it's not water flowing out of Lake Okeechobee. It's actually water being pumped into the canal from agricultural lands surrounding the canal. That's the negative values. So that remark is taken right from the USGS website. Because as soon as I saw that, I said, wow, that's sort of weird. Where does that come from? But luckily, they tell us that's where it's coming from. So let's look at our N members again. Here's June and July, so essentially the same time period as 2016. Now it's 2017, but a very different. We don't get the 3M members. Our runoff is not around, and really we're just seeing a nice mixing with a moderate Lake Okeechobee signaled, even though we don't seem to have much flow out of Lake Okeechobee. So just sort of general freshwater input is here, and then it's a nice mixing, and you can see that here's our South Fork and North Fork data is all the way up to about 25 to 28 PSU. So pretty regularly through June and July this year, in contrast to last year, seawater was penetrating pretty far up into the estuary. However, CDOM and phosphate is totally different. Well, our N member, the ocean, has not changed. That's nice to know that the ocean doesn't change in a yearly basis. But now, this is a different scale. So before we were on, I think, a 10 micromolar scale. Now we're up to 35. Here's the middle, here's the South Fork 2 data. Now we've got enormously high phosphate values, 25 to 30. My guess is this water, if it was totally fresh, would be really good to irrigate your garden with. Lots of phosphate. So we've really changed that whole system. Much more nutrients in 2017 than in 2016. Here's that same data, but on a time axis. And I'm going to speed up here. So basically, we got a lot more nutrients in the estuary this year than we did last year, but we don't have a harmful algal bloom. Just a quick contrast, here's last year's data on the same graph, and you can see it's all pretty much shrunken down. So lots more phosphate, but no HAB. That's our salinity-CDOM relationship. So again, what we're seeing here is that during this time period, we may have lots of phosphate, but we've got the salinity coming through, which means that the estuary is still acting like an estuary. It's acting like a mixing zone. It's flushing that material out to the ocean. Which, quick point here, there's a big difference between flux, which is the total amount of nitrogen moving, or nutrients moving through the system, and concentration. What we really, it's not that these nutrients aren't going anywhere. They're going out to the ocean, and will stimulate blooms off the coast, and that can can be its own problem. But at least in the summer of 17, within the estuary, our higher nutrient concentrations did not lead to a HAB, and that most likely that means that the residence time and tidal flushing is more important than nutrient loading. Okay, so now let's look at the end of this, which is Irma. So Irma comes through in September. They were dumping water before Irma got there, holding it during Irma, and then post-Irma, they've been releasing it pretty steadily afterwards. Okay, here's our September data set. Salinity-CDOM relationship. Now, here's a lot of fresh water coming through, and it's actually getting even lower in CDOM, so we're flushing lots of fresh water, hasn't been in the system long, has not accumulated a lot of organic matter. Now our CDOM phosphate relationship, now we're seeing much higher phosphate. Now note that North Fork is getting pretty high, it's up to 25, South Fork is up to 10, Middle Estuary is up to 10. So that water flushing through is making its way up into North Fork and then down into the Middle Estuary. And this is the data from last week. So let's go back to this one. So this is where I would say, oops, that's going to cause a problem. So we're starting to see that fresh water mixing, piling up at the triple juncture between the three basins. And this is the up to the minute last week, directly off the LoboViz site. Note that this is, okay, so this is salinity versus CDOM. Now our salinity scale, rather than 35, is only up to 4. And basically all of South Fork and North Fork is fresh water, and the Middle Estuary is barely getting into the brackish range. So again, lots and lots of fresh water. This is what we don't want to see for a HAB development. This is our phosphate loading. We've got plenty of phosphate in the South Fork. We're up to about 10 over the last week in the Middle Estuary, and the North Fork shows that nice sort of Dizzy Gillespie-like formation up here, where we see lots and lots of phosphate in the system. So that's what we were getting at the HAB. But finally, it looks like, well, this is the last week of discharge. In the last 2 days, the discharge has gone back to 0. So hopefully we will get enough flushing action over the next couple of days to get that fresh water, high nutrient loading water out, and the bloom will not develop. But it's a nice comparison and contrast between last year, this year, response of the system, both the human response and the natural response, and it will be very interesting to see over the next couple of days whether we see a HAB develop. And that's it, because it's live data, and it's an hour-old data. So there's not many more conclusions to say other than it will be cool to see what happens. So Abby, do I pass it off back to you?
Yeah, why don't you go ahead and leave up your presentation in case we have any questions. I just want to thank you for painting that picture of the HAB event with the IRLON data. That was really great. And since this is a smaller group, I'm going to go ahead and unmute everybody so they can ask you questions directly.
The conference is no longer in listen-only mode.
So if anybody has a question, just please go ahead and ask it to Ian directly. And I do have one from Megan Balling. What was the second summary bullet for 2017, please?
Okay, residence time. So for this summer, since there wasn't a lot of flow out from Lake Okeechobee, but we still saw very high nutrient values, that at least the first order hypothesis is that the freshwater flow out of the estuary was fast enough that we didn't get a harmful algal bloom growing up in the water in the estuary. So rather than 7 to 10 days in the estuary, which would lead to a bloom, it was probably on average getting out in 2 to 3 days. And I'm making those numbers up, so don't hold me to exact numbers, but that's the idea.
Great, thank you. Are there any more questions? All right, so I am.
Hang on, sorry, I was talking. I had my own phone on mute. So this is Jennifer Dorton, and I guess, have you all had much interaction with town or county officials or any other folks to present this data that might help them have a better understanding of what's going on in the Indian River Lagoon, and think about potential mitigation strategies or anything like that at this point?
So I presented a lot of what we learned in 2016 down at Harbor Branch, and also actually subsequently on the same trip over at in Fort Myers at the Sanibel Captiva Conservation Foundation. And while I was there, I did go and one of the county commissioners, or a couple of the county commissioners, and some of their staff were at the presentation. That presentation is actually still online at the FAU Harbor Branch site. You can go there and look at it. It got very positive responses, and there were Army Corps people there too, who basically said, yeah, that's pretty much agreed with what they were thinking also. So I think I was just reinforcing what they had already had surmised, but they were looking at it more from the hydraulics than from the biogeochemistry.
Right.
And that's my guess as to why they've continued that periodicity as much as they can.
It seems like it would be, and Abby, this is just me thinking sort of off the cuff a little bit here, that this might be a really good opportunity. If you're starting to see any changes in behavior, say at the planning and development level, based on some of this research, that might make a good sort of outreach piece or one-pager or something that SECOORA could help promote to kind of show that transition from research to applied science and decision-making.
Yeah, I'm not sure research is the right term. I tend to think of it more as like
monitoring,
observational journalism, or perhaps,
right,
or perhaps raw speculation, depending on what you thought of it.
Okay.
But yeah, no, I think it's a great case in which we've put data systems out there. We've provided live data. People have taken a look at it. It gives you an opportunity to make monitoring and management decisions on a much more rich data set than you can possibly have had before. And to my mind, that's why we're doing this. That's why we're doing the ocean observing systems. That's why we're doing the IUCs. It's not an academic exercise. We live on the edge of the ocean. We are changing the environment. We darn well better be measuring what we're doing.
That's a great piece of advocacy. We need to take you out to places.
I'm available for beers, that's for sure.
Jennifer, do you have anything else to add?
No, that was it. Thank you very much.
And Ian, I have a question from Mitchell Roffer. He asked, have you tried developing a predictive algae bloom model from this data set?
Okay. Mitch, no, but some bright young thing with a master's degree coming out of Harbor Branch should be, I don't know, setting up a competitor to you, or you could hire somebody yourself to do that.
I'm just interested. It would be nice to be able to predict this and warn people when something's about to happen. You see a lot of stuff on Facebook and social media, and it's hard to really know what's happening. And you look at the water; it looks terrible so many times.
Well, so I mean, you're a great case. What does Congress want to know? If we're funding these things, it's not this or that. How many jobs are we creating out of this? How much are we spending to put this data? I tend to think of this as sort of a development process in which the government-associated entities agencies are going to put out a guaranteed amount of information. It's up to other people, like you and your organization, to take that baseline data that we're going to put out 24/7, add your own analysis, perhaps add your own sensors, find people who subscribe to your processing, and sell that information back to them to create an economic good for everybody. So that then we're not just dealing with research, we're dealing with an ecosystem, a commercial ecosystem that's driving the whole endeavor. We can't drive models and predictive models out of academia or of government. We need to get them into the commercial space that answers people's questions, just exactly what you've been doing for your career.
Okay, thanks.
Are there any more questions for Ian?
Yeah, this is Kathy Fitzpatrick. I'm from Martin County. And I know, Ian, that you've talked about the importance of residence time. And I think one thing we need to look at is the data that was collected last year was in the summer, mainly June, July, August, when we had some pretty typical, fairly calm ocean conditions. What we're looking at now is trying to move water through the system, and it's coming up against exceedingly high ocean levels.
Yep.
So that the residence time is going to be increased because the water can't get, for lack of a better terminology, it can't get out the inlet.
Absolutely.
So I think that's something else to look at when you look at all this data is how you think about residence time and the forcing functions that are behind that too.
That's the entire game.
Great, thank you, Kathy. Any other questions for Ian?
My email is iwalsh@seabird.com. Feel free to email me, and I will not respond to you. But then email me again, and I will be embarrassed, and then I will respond to you.
And I put that directly in the chat box, and it will also be available online. All right, so I want to remind everybody that a recording of this webinar and a PDF of the slides is available at this SECOORA.org/webinar-series, all lowercase. If we could please save the date for the next webinar, October 24th at 12 p.m. Eastern. It was going to be performed by Nick Shea from University of Miami, but he is still recovering from Irma. So we're going to reschedule his date, so be on the lookout for a new speaker to be announced. All right. I want to thank you all for joining us, and we hope that you can join us on October 24th. And thank you again, Ian. This was really great.
Cool. Thanks, Abby. Thanks for the opportunity. Bye, everybody.
Thanks all. Bye-bye.